Okay, welcome everyone to EVPN deep dive session. We are still getting few people coming, more people interested in EVPN. That's cool. I'm so used to get the morning session, so I was keep repeating last few minutes that don't say good morning. So I passed first test. Okay, we are closing the doors slowly, so we can start. Most of the speakers are looking for like icebreaker initially. I don't have enough fantasy, so I'm using agenda as an icebreaker. You see that we have a really packed agenda. We have only 90 minutes, so obviously we will not be able to really go into bits and bytes on every single line from this agenda. But at the same time, what I can promise that if you will pay attention, mainly, let's say, first half of the session, you will understand the fundamentals. And you will then see that when we will go to more advanced use cases and more advanced examples, in the end of the day, we will keep repeating the same principles, right? So if you really understand the basic, how EVPN, ELAN, multi-point, all-active works, all these route types and everything, and we will really go into the details, you will then see the pattern. So it's keep repeating and so on. So really, if you will pay attention, mainly the first part of the presentation, you will get the fundament. Then we will focus a little bit more on the advanced part. We will also look at how to migrate from, for example, from VPLS to EVPN and so on. And completely last part, because in the end of the day, as I said, we have only 90 minutes. The last part is something I wanted to add something new, a little bit cool, which is kind of like interesting to do the control plane offload. We will see how much time we will have for this one. And then because some of the topics I believe are interesting, but unfortunately there is no way that we will be able to cover them. Therefore, I put it as an offline learning. So you will get it with the slides. If the slides are not available right now, don't be worried. The slides will be there later on, so you will get everything. You don't have to do the print screens or making like the pictures. Everything what you will see here, you will be able to download. You will be able to get it. So let's go for it. So first of all, whoever attended any of my session probably saw this slide. I really like to show this first slide because it will basically show you the journey which we were taking. If you will go back to 2016, 2015, when we were really starting the EVPN with IO6R, with MPLS data plane. The one thing which is very important when we talk about the service provider environment, we know that most of the deployments are brownfield. We cannot, greenfield is really nice, it looks nice on the slides, but in the end of the day, you need to be able to integrate. If we will look at like what today we can take as a legacy, right, or let's say more old protocols, how we were building the networks before, the obvious difference was between the data center and the service provider environment. The data center, in the end of the day, IP transport, later on VXLAN with the EVPN control plane on the top came as the first because EVPN was like a more natural initially to the data center. And obviously, then with certain benefits, we were bringing the EVPN into the service provider network as well. We were all used to for VPLS, and we know the challenges with the VPLS. We will also talk about it, and which challenges we are trying to basically, or we are fixing with EVPN, and where EVPN makes sense to go into the service provider environment. But very important part of this picture, if you will look at, is like we are trying to really find the way how the network will be really end-to-end, like single network, right? Before, if you will look at data center, always completely different encapsulation, completely different protocols, completely different products, and so on, right? Compared to the service providers. And in the end of the day, today we can see more and more demand to basically be really much more like interconnected. And you can also see the DCI device there. This is like a lot of mystery around, and I will also try to clarify why DCI and where DCI makes sense, what we actually wanted to do with the DCI when we started to talk about EVPN. But the most important is that you will see that suddenly we can use a single control plane for signaling any type of the service across data center, service provider core, service provider access, and so on. And it's a BGP. It's not only BGP EVPN, it's BGP. I will keep repeating it all the time because you will see where it makes sense to talk about EVPN address family and where it makes sense to still continue, for example, with VPN v4, VPN v6, and so on. And we will really go over these details, and we will try to make it clear. So first, what we are trying to achieve, right, over the time. We know that when we started with the VPLS, with MPLS, MPLS transport, MPLS type of the services on the top of it, when you look at the protocol stack on the left side, you have some IGP, LDP. On the top of it, if you want to do traffic engineering, you are using some RSVP-TE, and then you have typically BGP-LU for inter-domain LSP, and for services, we are using LDP or BGP for the signaling, right? If you will look at UMMT design or seamless MPLS, it's very popular design in the end of the day. It's a quite old one, but managing this protocol stack is actually quite difficult. The first simplification came from the transport. We brought segment routing with the IGP, so we were able to remove the LDP, we were able to remove the RSVP for traffic engineering. We are still keeping the BGP-LU for inter-domain LSP, and we were unfortunately keeping still LDP and BGP for the services. And what we will be focusing right now in this presentation is basically the last part, where BGP will be only single control plane for signaling any service. In the end of the day, if you will have L2 VPN service, L3 VPN service, you will be using the BGP. What is the key benefit of having single control plane? Obviously, simplicity, that you have single one. But then when you will want to do basically you will want to tie your service to the, let's say, programmable network, you will have certain SLA. You can provide any SLA to any type of the service. It's not anymore I have a certain SLA for L3 VPN, I have certain SLA for L2 VPN. I can basically really unify. I can provide single type of the SLA across any type of the services. I promise that we will go and we will look at why makes sense in service provider environment to think about EVPN and where the EVPN makes sense, or basically what we are bringing on the top of the VPLS. Because obviously, if you have existing VPLS, you want to know why it makes sense to think about EVPN control plane. So first thing, what EVPN is solving is multi-homed access. Right? If you will look at with VPLS, if you want to do multi-homed access, you have to use some multi-chassis lag, or you have to use some proprietary protocols. From Cisco, it will be cluster, VSS, VPC, and so on, right? Or if you will want to have a hierarchical VPS, you will have active backup pseudowire. It's never really active. You have to really care that in the end of the day, you will protect the loop from, which is basically coming a frame from one side into the, let's say, PE1, and then sending it back on the PE2 back to the access and basically creating the loop. This is something what VPLS as a technology is not solving, right? So this is the first thing what we are solving with the EVPN, and again, we will go over the details to explain how exactly EVPN is solving this problem. So very often I'm also saying that EVPN can be multi-chassis protocol. Basically, will help from this point of view. Look that P1 and P2 are like a single device in the end of the day from the CE point of view. The second problem here is that if you will have a multi-homing, right, because VPLS is nothing else than full mesh of the pseudowires. So if you will ingress replicate, or if you will send broadcast, anonymcast, and multicast traffic across the L2 domain, so basically you will flood it. On the remote side, in this picture, PE3, PE4, both of them will basically send it into the access, and you will have a duplicity. So this is another thing you need to take care with the EVPN when we will start to migrate, and we will explain. And completely last one, which is not always obvious, is MAC address flip-flopping. MAC address flip-flopping will happen when you have a full mesh of the pseudowires, which is VPLS, and imagine that the same source MAC address will first come from PE1, second time it can come from PE2. So remote router PE3 will first learn the MAC address from the tunnel which is coming from PE1, then from PE2, and you will keep rewriting all the time. EVPN is again taking care of it. We will introduce the concept Ethernet segment, and we will talk more about it, how exactly EVPN is solving this problem. So these are very key three benefits of EVPN when we will go into the VPLS and how we will want to solve this problem. And obviously, you will see much more when we will be moving ahead. I hope that for a lot of people it will be like, okay, why we see this basic picture? We have like BGP signaling, we know how to look MPLS packet and so on. I think that is what is really important to understand why L2 is more difficult than L3 in some of the use cases. The beauty of L3 is that your CE has a typically BGP session with your PE router. So your CE will tell you, hey, I have these prefixes. I have it here, I'm alive, and I have these prefixes. If you will look at L2, you don't have this luxury. In L2, you are just connected, and when you have some L2 network, like legacy network, you will have spanning tree or GAT32 or REP. You will maybe receive the TCN, like topology change. Something happened, but you even don't know what happened. You don't know which MAC addresses are there until you will learn the MAC address somewhere. And that's a challenge because when you will start to do the multi-home network, basically from this PE1 and PE2 point of view, when you want to protect the loops, you need to have the central mechanisms, to basically understand how the L2 network behind these two routers looks like. And we will talk about it. So the basic principles. The first thing, what EVPN is trying to do, we are trying to do integrated layer 2 and layer 3 together. So we will talk about like layer 2 first, like how it looked like, then we will talk about IRB, integrated routing and bridging, and why it makes sense, and why it makes sense mainly in the data center. What was the key reason? Very important thing, EVPN is not trying to reinvent the wheel. We are really trying to take as much as possible we invented for L3 VPN, and basically reusing it. And obviously, we have to add some tricks on the top of the L3 VPN to protect the loops, take care of the L2, because again, L2 is unfortunately a little bit more difficult. But I'm very often saying that if you don't completely understand how exactly this part works in the BGP, do the step back and think how it works in L3 VPN, and you will very often find some connection that there is some basic, like the key principle which they are sharing. All-active multi-homing. We will be covering most of the time all-active multi-homing because it's the most important use case. We will go into the details. Then when you again really look at it like next couple of lines, this is what I was describing on the previous picture. We want to have a BGP control plane. We don't want to have anymore the full mesh of the pseudowires because of the multiple reasons which we will go over it. We want to optimize the broadcast and unicast and multicast traffic. And very important, EVPN is NCAP agnostic. It means you can use MPLS, you can use the VXLAN, you can use SRv6. Our examples will be mainly with the MPLS, but in the end of the day, same principles applies to VXLAN and SRv6. And in the end of the day, there are really small details, and we will touch some of them. EVPN from the MEF point of view is covering also basically any type of the L2 services like EVPN ELAN, EVPN E-line, E3, and so on. We don't have anymore this auto-discovery because in the end of the day, everything is BGP, so everything is auto-discovered. There's no separate auto-discovery and signaling. Everything is basically just the BGP. And obviously, support of the IPv4 and IPv6. And the last line from my point of view is the most important. If you will look at it's not very often that industry really agree, basically all the vendors, the customers, from the standard point of view. We will go and we will really agree that for some part of the network, the protocol is the protocol for the future. If you look at it, EVPN doesn't have a competition. There is nothing like EVPN that someone is trying to say, hey, this protocol will be better than EVPN. In the end of the day, there is a consensus on the market, on the industry, that EVPN is the protocol for the L2 VPN and sometimes also for L3 VPN services. This is quite unique because in the end of the day, we typically have multiple protocols and we have a competition between the protocols. Very quick summary from the encapsulation point of view. When we will talk about EVPN, as I mentioned, we will have example with the MPLS. I will be focusing on the MPLS. But at the same time, as I said, it's, in the end of the day, agnostic. The most popular protocol, or most popular encapsulation, MPLS VXLAN, and later also SRv6. If you will want to learn more about VXLAN and SRv6 data plane, you can definitely find the sessions here as well, or even like then study offline. The most important here is that we will basically encapsulate all the Ethernet frame into the MPLS or IP header and forward it over the transport. This is for L2 VPN services. Then for L3 VPN services, obviously we are encapsulating the IP portion, and we will also talk about like how EVPN is playing the role in the L3 VPN services. And also I will come back to my original comment that EVPN and VPN v4, VPN v6 are actually the friends that very often they can work together, and they are really not competing. Sometimes I can hear that should I replace my VPN v4, VPN v6 signaling by EVPN signaling? We will see that most of the time it doesn't make sense, and it completely makes sense to basically use both of the address family. We will talk about the details. Important part here, when you will look at the VXLAN based on the standard, you need to have inner Ethernet header. That's very unique for VXLAN. Obviously, there is also GPE type of the encapsulation, which is saying that you don't have to use the Ethernet header, but be aware that for the standard VXLAN RFC 7348, you need to have inner Ethernet header for the transport. Key concept, very important is that, again, I mentioned that in service provider environment, most of the stuff is a brownfield, right? So if I want to go and I want to introduce the new technology, very often I need to find a way how I will seamlessly integrate it into the existing part. If I will not find this, it will be very hard to deploy, right? We know how it works in the service provider environment. Data center is obviously much easier because migrate the whole data center to the new technology. It's definitely much easier, especially because of the size and also like where exactly are the devices located. So if you will then, and you will see the configuration example, we will see that we have, when you talk about L2, we have still bridge domain, which is basically like a virtual switch. We have attachment circuit, and we have some core interface port, which is basically facing to the core network, to MPLS core network in this case. If you remember how looks the configuration with the VPLS, we had the VFI interface into the core. In this case, we will have EVI interface. And we will talk more about like how exact is the configuration. I just want to make here the note about that basically from configuration, from provisioning point of view, the key concept will remain the same to basically allow you to do really seamless migration from the VPLS to EVPN. And we will have also this example later on in the slides. Ethernet segment. I mentioned Ethernet segments only once, but you will be hearing the Ethernet segment all the time, because this is the most important when you will start to do the multi-homing. Here in this example, the C1 is single home to P1. It's boring. You don't need to take care too much stuff because there is no multi-homing, so there is no loop, easy loop between the C1 and back to the C1, which you can introduce. But where it started to be interesting is the CE2. C2 is multi-home to P1 and P2, right? So you need to start to play like basically P1 and P2. They need to know that basically they are sharing the same broadcast domain. And as we said, like we don't have any protocol from the CE which will say, hey, this is the same broadcast domain. So we need to somehow figure out that it's connected into the same one. And in this case, you as an operator, you are responsible to configure the same Ethernet segment for the same broadcast domain. So basically P1 and P2 will configure same Ethernet segment towards the CE2. And then you will see in the BGP signaling how this Ethernet segment value is important for a lot of negotiation, which they will see, and basically a lot of programming also of the forwarding. We have a lot of BGP routes here. EVPN has a lot of flexibility. Today we have more than 5 BGP EVPN routes. We have also route type 6, 7, and 8. This is then for multicast, but today we will be covering the first 5. And as I mentioned, if you will really understand how first route type 1, route type 2, 3, 4, and 5 works, you will understand the basic concept. And in the end of the day, everything else is really add-on. So really, it's important important to understand the first 5 BGP routes. And obviously, every BGP route has an extended community. We will also touch this part as well. Now, what is the most important for the multi-homing? Really decide which type of the load balancing I want to do. EVPN knows the 3 basic multi-homing or load balancing multi-homing use cases. The first one is all active. All active is probably the most deployed one. Every time in the data center you will be deploying the all active. I'm always saying that if you can deploy all active, go with the all active because you are getting most benefit of the EVPN. And it's nothing else than from this point of view, you have a transparent bundle on the CE towards the P1 and P2, and basically P1 and P2 are pretending to be like a single device. And we will talk about like how exactly they can pretend to be single device, because then you have really per flow load balancing. This is something what you didn't have before with the multi-chassis leg and so on, because, for example, multi-chassis leg was per VLAN load balancing or active standby. The single active is the use case where you want to, for example, enforce QoS. Right, because in the first example, all active, if you want to say that the CE can download only 1 gigabit of the traffic, in the end of the day, it's very difficult to do it, right? Because the traffic can be balanced over 2 Ps. It will be challenging. So basically, with this one, you will do something like per VLAN load balancing. So P1 will be active for VLAN 10, P2 will be active for VLAN 20. Right, so basically you can share per VLAN, something like pseudo multi-chassis LAC. Then port active. Port active is a really use case where we talk about active standby. So in this case, again, configuration is similar like in case of the all active, but P1 and P2, they will agree who is basically active and who is standby. And the standby device, in this case, PE1, will send over LACP out of sync. So basically, from CE and from the PE point of view, the link between P1 and C3 will not be ready to forward. Right? So basically, it's really like, from EVPN, it looks like single home. When this link between C3 and P2 goes down, the link on the P1 and between P1 and C3 will basically come back. Now, what is the difference between single active and port active? If you will think about it, it's kind of like active standby and so on, where you should think, where you should deploy one. What will be the rule to deploy this type of the load balancing modes? Again, the first one, if you can go with the all active multi-homing, is the best one. You will get most of the stuff from the EVPN, you will get the balancing, you will get the better convergence. In the end of the day, this is the best load balancing mode. When you need any active standby, and you know that later on you will be migrating to all active, it's much easier to go with the port active, because migration from the port active to all active doesn't require the touching the CE. Look at the detail of the CE. In case of the port active, we have again transparent bundle, and only one link is not ready. So basically, because of LACP out of sync, as I mentioned. But in case of the single active, I have 2 separate uplinks. I have 2 separate bundles, because I need to be able to flood on the both sides, and only one side is basically active. And we will see the details. So if you want to go from single active to all active, you have to reconfigure the P1, P2, but you have to also touch your CE, because you need to configure transparent bundle. When you will want to go from the port active to all active, you're just touching the P1 and P2. And we know that very often, touching the CE is a very difficult part. Let's go to the details how basically the EVPN works. Right? So first, in the examples, you will see sometimes like PE, sometimes like the leaf. But in the end of the day, if we will think about MPLS encapsulation, leaf and PE is completely the same thing, right? Then when we will talk about P router versus spine, what is the difference when we have an MPLS? It's the same thing, right? So it's just a terminology. If you don't like a leaf, in the next example, translate in your head into the PE and vice versa. In the end of the day, it's just a terminology when we will discuss these basic principles. Okay, Ethernet segment, again, I promise that Ethernet segment will be there all the time. So Ethernet segment, if we will take this basic topology, basic example with the 4 leaves, that leaf 1 and leaf 2 is, they are multi-homing the compute 1, and L3 and 4 are multi-homing the compute 2, right? You can run the VMs there, containers, that's not important, but they are doing this multi-homing. L1 and L2, they will have one Ethernet segment. So again, you as the operator, you will go and you will configure the Ethernet segment for this link for L1 and L2. The same thing, it will be L3 and L4. The first, what you can ask, okay, when I will do mistake, and I will configure by mistake like the same ESI on basically on the link L1, L2, L3, and L4, in the end of the day, the EVPN network will think that they are basically multi-homing like the single compute. So obviously, you will not have any forwarding between compute 1 and compute 2. Therefore, I'm saying you have to be very careful when you are configuring the Ethernet segment. We will see some show commands how to verify that you configure this properly, but mistake of configuring the wrong Ethernet segment will basically cause that, in the end of the day, EVPN doesn't have a clue what is multi-homing, that basically there is multiple devices, and you can directly introduce the loop. Yes, please. Okay, the question was, there is a 10-byte global ESI, and question is, why the first byte is a 0? If you will go to the RFC and you want to configure the static ESI, statically, the first byte is a 0. It's type 0 configuration. So basically, first you configure 9 bytes because you know that the first byte will be the 0. Then it's a different type of the ESI, like auto-generated ESI. For example, you can auto-generate from the LACP. There was initial idea to use the auto-generation of the ESI from the LACP. Unfortunately, we are strongly not recommending to use it because you can run into the certain race conditions. We always recommend to configure static ESI because there is a problem. If the link goes down, you cannot trust that when the link will come back, you will receive the same LACP MAC on that link, right? Because someone could just use this link and reconnect to the different CE. So you have to go and you have to withdraw everything from the data plane, everything from the control plane, and every single time when the link will flop, you have to go completely through the new cycle of learning, programming, and so on. So you have a problem typically with the convergence. In the end of the day, the best thing and recommended solution is to really configure the ESI statically. Type 0, it's a type 0, ESI type 0. No, if you are configuring the ESI statically, it's a type 0. We can then talk offline, like at the end of the session. So then, most important, if you are learning the MAC addresses, right? Because we are talking about L2, we talk about ESI, it's starting to be like, come on, where we will start to learn the MAC address, right? So let's say that all on the L1 and L2, you will learn from the compute, you will learn the MAC address of the VM, for example. Let's say you will learn it on the L1. Now you will advertise this MAC address everywhere. Completely same, you would advertise the prefix when you would learn the prefix in the layer 2. In the layer 3 VPN. It's very important to understand that basically this advertising of the MAC address has two reasons. One reason is obviously reachability. You want to L3 and L4 understand that this MAC address is behind L1. But it is also the synchronization reason. You will use the same route also to synchronize this information between L1 and L2, because you don't want L2 to send the traffic to L1 when it's for compute 1, because L2 is also connected to the compute, right? So basically, what you will do, you will say, hey, this MAC address on me, I'm advertising this MAC address, which means I learned this MAC address, but I learned this MAC address from this ESI, let's say ESI 1. This route type 2, which is for advertising the MAC address, and we will see the details, when it will arrive on the L2 will look at the route and say, okay, it was learned from the ESI, which I also have connected locally. I'm not going to use it as a reachability. I'm going to use this route for synchronization, and I'm going to point this MAC address to my local interface. So basically, with this, I will synchronize the forwarding information between L1 and L2. Completely same thing will happen between L3 and L4. On the other side, if you will think about it, L3 and L4, they will receive this MAC address of L1. Let's say that because of the balancing of the compute, the traffic is all the time from compute going to the L1, because there is like very basic balancing which you are not able to control. The L2 will never learn this MAC address, right? The problem is that, but at the same time, I know that I can balance between the L1 and L2. And this will help me. This ESI will again help me to achieve something like this, because L3 and L4, they will know, and you will see from control plane, that this ESI1 is connected to both L1 and L2. L1 advertises the MAC address with the ESI1. So basically, I can do another indirect lookup, and I will see that I can balance over the both. And you will see we will go into the packet flow to basically really understand these details. So let's take a real lab. Basically, we have like this very similar topology which we had in the previous picture. We have two hosts which are multi-homed, and we will go over basic configuration. The first one, if you are using LACP, you have to configure the same system MAC on the two nodes which are multi-homing the host, right, or CE, because both of them are sending the same LACP system MAC. In the end of the day, there is no any synchronization. You don't need to synchronize anything between LACP. Both of them are sending the same, so they will just configure the same MAC address. If you want to configure the instance, which is basically like this core interface in the bridge domain, you will configure EVI ID here, and you will say advertise MAC. Advertise MAC will trigger the advertising the MAC address, route type 2. We will go over the details. And then most important, you have an interface, and you configure the Ethernet segment. You will see here that it's type 0, and you are configuring this night byte value for the ESI. So again, this is the one which you have to be careful, and you have to configure the same ESI on the both nodes which are multi-homing the same host. And then when we will go to the L2 VPN configuration into the bridge domain, we have a interface, which is my attachment circuit, and then I have an EVI port, which is basically telling me which instance I want to use here. That's it. Not completely, because I'm still missing the BGP. If you will look at the BGP configuration, it's very similar to L3 VPN, right? You have your BGP router ID, except address family VPN v4 unicast. You will have L2 VPN, EVPN, right? And then I have my configuration of my route reflectors here. If I'm using route reflector, typically you will use a route reflector, but in the end of the day, it's very straightforward configuration from the BGP point of view. There is one very important principle for basically preventing the duplicity. You remember when we had the original picture, we said that in the end of the day, when I will not be able to protect, basically I will not be able to decide who is sending the broadcast, unicast, and multicast traffic back to the access, I will have a duplicity or I will have a loop. One of the key principle which we are using in EVPN is the DF election. DF election works that basically between L1 and L2, they will basically, for instance, they will agree who from these two will following broadcast, unicast, and multicast traffic back to the access. Why? Because the broadcast, unicast, and multicast traffic is typically flooded inside the core. So let's focus on L3 and L4. Let's say that L1 received a broadcast, destination MAC address FFFF. L1 will basically ingress replicate in case of the EVPN on IO6R. We are ingress replicating with MPLS data plane. So let's look at what will happen on L3, L4. Let's park for second L2. L3, L4, both of them will receive this broadcast traffic. Normally, both of them would send it back down to the C2. In this case, because it's a broadcast traffic, they will agree that only one is forwarding the broadcast, unicast, and multicast traffic to the access. So basically, we call this DF election. How DF election works? L3 say, hey, I'm using this ESI. L4 say, I'm using this ESI. Both of them, they will see that they are not alone in the network, and both of them will run the DF election algorithm independently, and basically will decide if they are DF or not. So there is no some additional TCP session which will do like handshake or something like this. No. I'm advertising the ESI, someone else is advertising the ESI, and then based on this, I will do my own calculation if I'm the DF or not. Basically, part of the route type 4, there is also like signaling type of the algorithm which I want to use. By default, we are using the algorithm like the modulo, so which means that I will basically take the EVI ID, I will do modulo 2, because typically I'm doing the dual homing, and if I will get 0, the router with the lower BGP router ID will be the DF, and in case the result modulo 2 will be 1, the router with a higher BGP router ID will be the DF. So if you will think about it, you will get to the point that you are getting the EVI ID odd and even, like numbers, right? Same thing like the VLANs, right? The VLAN 10 will be active on the P1, VLAN 11 will be active on the PE2 when you will be following the same ID with the EVI. If you want to know who is the DF, you will just go and you will do show EVPN Ethernet segment EVI, and you will put the Ethernet segment carving details. And when you will look at the detail in the route, you will see who is elected for the particular EVI. So basically here, in this case, router 36 is elected for EVI 100. Obviously, router 36 will not be elected for EVI 101, but will be elected for 102, again, because we are using the modulo for this one. Very important, if you want to see the BGP route, for basically the DF election, we are using the route type 4. Again, route type 4 is nothing else than advertising saying, hey, I'm using this DF. If you will go into the detail, you show BGP L2 VPN, EVPN, RD, which is your route distinguisher, and you will then see the detail of the route. You will see that it's route type 4. You are getting this Ethernet segment, right? And also, like, you are getting the EVPN import like a route target. You will see the route target here in this case is you will see that it's part of the ESI. Why? How works a route target in L3 VPN? I'm doing import and export certain route target. If VRF1 wants to import the routes from another PE, which are also part of the VRF1 or VRF8, I will just do import of the route target which was exported on the other side. In this case, because I'm doing the DF election locally between just the two devices, because they just have to decide who will be the DF, I don't need remote routers to know about this route type 4. This is only local information. So what will happen here is that I will auto-generate the route target. Basically with this route target, I will do export and also import. And this route target is auto-generated from part of the ESI. So in the end of the day, it's a very straightforward process. Basically, EVPN process will take portion of the ESI and will generate this route target. The bump traffic. We said that I will receive the bump traffic, but at the same time, we need to somehow signal this information, how to basically start to forward, right? Until now, I didn't get any reachability information. I know the ESI, I have a DF election, but I never said that when you want to send me the broadcast and unicast and multicast traffic, use this particular label when we talk about MPLS. So for this one, we are using the route type 3. The route type 3 will, again, when we will look at show BGP L2 VPN EVPN, we will use the RD of the router. We will see the details. That route type 3 is here. We will see the extended community, which is a route target. You will see the different route target than we saw, for example, for the route type 4. This route target is completely same like when we talk about the VRF, right? If you go into the VRF and for L3 VPN, you will configure your route target 1:100, which you will use for import and export. In case of the EVPN, the beauty is that for this, basically like the per EVI routes, which is route type 3, I'm doing by default the auto generation. I configure my BGP in my lab with the BGP AS1, and we have EVI ID 100. So by default, I will auto generate the route target 1:100. You can obviously go and you can override it, but you want to be sure that basically this thing will be the same across the EVI 100 on the all routers. And you will see we will then go into the packet flow with the more details. Type 6 is basically saying how I'm gonna deliver this broadcast, anonymous, and multicast traffic. Route type 6, based on the RFC, is saying that it will be ingress replication. So it means that I'm expecting that this traffic will be ingress replicated to me. And finally, the value of the label, basically for the bump traffic. Now, why I need to have specific label for broadcast, anonymous, and multicast traffic? The reason is very simple. If the traffic will arrive, if you go back and you remember that we have to do the DF, right? Only the DF is forwarding this broadcast, anonymous, and multicast traffic back to the access. I need to know that it was actually the broadcast, anonymous, and multicast traffic. For the broadcast, it's simple. I will look at the destination MAC address and see this FFFF, and it's very simple. I can decide that it's a broadcasted. Multicast is also multicast MAC address. It's very simple. But what about unknown unicast? For unknown unicast, I can get to the point that someone didn't know that MAC address and basically was flooding inside the L2 core, but at the same time, for me, it's a unicast because I know about that MAC address, right? You cannot rely that your network is 100% synchronized all the time, right? There can be delay in the BGP signaling and so on. So therefore, when you will use the extra label, this extra label will tell you, hey, by the way, on the other side, on the ingress, someone ingress replicated this traffic. So I don't have to think about it. When I see this label, because I advertise this label, that I want to receive any ingress replicated traffic with this label, I know that I have to apply the DF election rule. I have to say, I'm forwarding this traffic to the access only if I'm DF elected. If I'm not, I have to drop it. So that's a key reason. Now we skipped, you remember I said, let's park for a second the L2, right? We said we are ingress replicating to L3 and L4, but not to the L2. What will happen here? So obviously, I have to again send the bump traffic, which I will receive from L1, I have to send it to L2. And in this case, we want to be sure that L2 will drop that traffic, because otherwise, it would be the loop. But is the DF election actually good enough in this case? No. The DF election work only for remote pairs, not on the local pairs. If I'm multi-homing the same Ethernet segment with L2, I have to use the different mechanism. Why? Because I'm not able to control, how compute will balance the traffic, right? So let's say in this case, L1 is a non-DF. But L1 will receive this broadcast, anonymous, or multicast traffic. I cannot drop it. I have to accept it. So I will accept it. I will send it to L2, ingress replicate to L2, and L2, because it's DF, will send it back to the access, and I have a loop. So DF election doesn't work for local peers. So for this one, we are using extra label here. We call it split horizon label. So what will happen, when L1 will receive broadcast, unicast, and multicast traffic, will again ingress replicate on the remote side with their particular BUM label, right, from the route type 3. But in this case, we'll use the BUM label of the L2, but we'll also use the extra label, which we call split horizon label, for this particular ESI. And we'll send it to L2. When the L2 will receive it, say, okay, I know it's a broadcast, unicast, and multicast traffic, ingress replicated to me, but I also see the split horizon label for my ESI, so I know that I cannot send it here to this particular link. Obvious question will be, okay, why we are doing this complex thing in the data plane where we know that L2 will drop the packet? The answer is very simple. I can have also another device which is in the same bridge domain and is single home to the L2. So we want to send this bump traffic, which is, for example, coming from the compute 1. We want to send it to L1. L1 will ingress replicate to L2. I want to be sure that it will not go back to compute 1, but it will go to compute 11 in this case. So split horizon label is also per ESI. So when I will receive the data plane traffic, again, I will see it's a BUM, because I'm in there, the BUM label, but I will also see the split horizon label for this particular ESI, for ESI towards the C1. So I know that I will not send it back to C1, but I will send it to C11. Yes, please.
Does this label show up in the MPLS forwarding tables already?
No, you will not see this label in the question. I'm sorry. The question was if I will see this split horizon label in the MPLS forwarding table. You will not see this in the show MPLS forwarding. No, this one is not there. There is only BAM label and there is the transport label. It's not this one. You will not see there. So the next one, the question is how I will actually signal this split horizon label. Before I will go to signaling the split horizon label, because we will show the route type 1 for it and so on. Let's introduce one more concept, which we know in EVPN and which is very unique to EVPN, and it's a mass withdraw. Imagine that you have the compute where you will have, let's say, 10,000 VMs, so 10,000 MAC addresses. Right? And you have all redundancy, you have all active multi-homing, L1, L2, L3, L4. So basically, when you will lose the link, you should see very fast convergence and so on. The problem here in this case is that we are using the control plane for the signaling, right? It's BGP. So this L1, advertised the 10,000 MAC addresses, right? Route type 2. MAC address 1, MAC address 2, MAC address 3, and so on. We also know that we are using the ESI to basically tell, hey, this MAC address is coming from ESI L1 and L2, so you know that you can also send it towards the L2. But on the other side, L3 and L4, they are like saying, okay, this MAC address is available over L1, this MAC address is also available over L2. And imagine that you have 10,000 MAC addresses. And you will start to go, because you will lose this link from L1 to compute 1. So L1 will start to withdraw the MAC addresses. Hey, I don't have any more MAC address 1. I don't have any more MAC address 2, MAC address 3, MAC address 4, MAC address 5, and so on. BGP, obviously, will take some time to withdraw all these MAC addresses. So when you will be, unfortunately, the MAC address, let's say 10,000, during that time, you can have a still problem that L3 and L4 are still forwarding the traffic towards L1, and L1 will be dropping. So EVPN has a concept of the mass withdrawal. Because we have, again, ESI. So indirection is that MAC address 1 is pointing to ESI 1, which is L1 and L2, and this is behind L1 and L2. It's a single route. It's telling, hey, ESI is sitting here behind L1 and behind L2. So when you have the failure of this link between L1 and compute 1, L1 will withdraw single route and telling, hey, by the way, I don't have ESI 1 anymore. I lost ESI 1. So remote router, L3 and L4 say, okay, I don't have ESI 1, so all these MAC addresses, which is not only MAC address 1, but let's say MAC address 1 to MAC address 10,000, is pointing to ESI 1, but ESI 1 is not behind the leaf 1 anymore, it's only behind the leaf 2. So you have only single route withdrawal. Yes, please.
What happens if you don't use ESI rather than use port? Is it similar?
Please repeat it one more time.
If you don't use ESI and we use only the port from the CC1, it's a similar behavior?
The question is, well, when we will not use the ESI here. ESI has to be used when I'm doing the multi-homing, right? I don't have to use the ESI when I'm doing the single homing. In that case, yeah, I will not have a mass withdrawal, but the problem is, if I'm using the single homing, do I actually need a mass withdrawal? Because single homing means that, the device which is connected to me, is anyway not reachable. So if the convergence will take like 5 seconds, 10 seconds, I don't care, right? But in the end of the day, even if you will have a single home device and you will want to have a mass withdrawal type of the behavior, you will configure ESI. So if you configure ESI, doesn't matter if it's all active or is it single home, in the end of the day, it will work completely same. Okay. We talk about split horizon label, we talk about mass withdrawal. The reason why we talk about this too, and we didn't show any route, is that we are using the single route for both. Basically, there is route type 1 per ESI. Route type 1 per ESI is for advertising, basically, again, ESI, which ESI I'm advertising, and is saying that which type of the balancing I'm using. Here, in this case, when it's 0, 0, it's all active. When it's 0, 1, it's a single active. So basically, remote side knows if both of the nodes can forward back to the access or only one can forward to the access. That's one information. And another one, which is very important, is this split horizon label what we talk about. So basically my peer will receive this split horizon label and will know that, hey, by the way, if you received the broadcast, unicast, and multicast traffic from the same ESI, which we are here multi-homing, be sure that you will impose this split horizon label, because when it will come back to me, I will not introduce the loop. And same route we will use for mass withdraw, because this route on the remote side is saying, hey, I have this ESI connected to me. So I will do withdraw of this one route type 1 per ESI, and basically remote side knows that this ESI is not available anymore. A lot of information. Let's right now do the packet flow. Let's put everything together. Let's be sure that we are on the same page. Let's go back to the lab. What we have here, like router 36, 37, 8, and the 9. So first of all, I have to do the DF election between 36, 37, 38, and 39. So first what will happen, I will advertise route type 4. Both of them, 36, 37 say, hey, I have this ESI. 38, 39 say, I have this ESI. And they will run the DF election. If you remember, by default, the algorithm is the modulo algorithm. Basically, I will take EVI ID modulo 2 because I'm doing the dual homing. 0 will be the 36 will be the EF, 1 will be 37, the DF, based on the BGP router ID. The second step will be that they will advertise this EVPN route type 1 per ESI. So as we discussed in the previous slides, route type 1 per ESI is there for mass withdraw, to basically signal, hey, this ESI is not connected to me anymore. You cannot send any MAC address which is pointing to this ESI to me. That's one thing. And second thing is also to protect basically the loop between 36, 37, 38, 39, basically for the broadcast, unicast, and multicast traffic. Next one is that I need to signal the reachability information for broadcast, unicast, and multicast traffic. Basically, I'm saying, hey, if you are sending broadcast, unicast, and multicast traffic, use this particular label, something like VPN label. And this I'm advertising through route type 3. How then it will look like? Let's say I received the bump traffic from H1 here. So basically H1 is sending the bump traffic to 36. I will take a transport label of the 38. I will take a bump label of the 38 for EVA 100, and I will put their original bump, and I will send it to router 38. I will then create another packet where I will take the transport label of 39, and I will put there the bump label of 39 for EVA 100, put there the original bump, and will send it to 39. Basically, both of them, 38, 39, both of them will receive it. What will happen with the 37? I will again take the transport label of 37. I will take a bump label of 37 for EVA 100, and I will add this split horizon label for this particular ESI. I will again put there this bump traffic, and I will send it to 37. 37 based on the bump label, based on the split horizon label, the red one will basically drop the packet because will not send it back to the H1. Similar thing will happen on the remote side of 38 and 39, based on the DF election, only one will forward this traffic to the access. So it's very important to remember one thing. DF election work on the remote side. To protect local loop between 36, 37, I need a split horizon label. And obviously same will be from the opposite side between 38 and 39. That's important to understand that DF election is really for the remote. Okay, until now we talk about the broadcast and unicast and multicast traffic. Now, what is my unicast information? Unicast like forwarding information. It's a route type 2. When I'm advertising the route type 2 MAC address with the ESI, I will also advertise the label. So basically, I have a label like reachability for the unicast traffic. So every EVI, every context will have two forwarding labels, one for BAM and one for unicast traffic. If we will go back, into the previous picture, and we will look at like, why I'm doing the DF election on the 38, 39. Because I know when I received the traffic with the BAM label, I know that not only me, but also my peer is receiving this traffic. So I know that only who is a DF, the router who is a DF can forward the traffic. In case of the unicast, router 36 will decide, oh, I will send to 38 or 39. So in this case, both of them are forwarding into the access. They are not applying the DF election rule for unicast traffic. So therefore, I have two different labels, one for unicast and one for multicast. So for unicast, there is a balancing. You are utilizing both of the links. Only for BAM traffic, you are basically not utilizing both links because only the DF will forward to the access. If you will want to check the MAC addresses which you learn and which you advertise, you will go and you do show EVPN EVI MAC, and you will basically see all the MAC addresses, and you will see the next hop, right? So here you see which router, which label forwarding of this MAC addresses. Really, route type 2 is something like the VPN v4 route. So then let's look at how we looked at the unicast. So I received some unicast frame. I learned the MAC address of the H1, and I will advertise the route type 2 for the MAC address, again with the ESI, particular MAC address label, and also route target of the EVI. As we discussed, by default EVI is route target of the EVI is auto-generated from BGP-AS. In my case, I configure BGP-AS1, column 100, which is EVI ID. You can override this value, it's just auto-generated. So then when we will have a forwarding of the unicast, what will happen here, that when the traffic is coming back, where the destination MAC address is of H1, we will take transport label of the 36, because we learn it from 36. We will take label, which we learned from the route type 2 for MAC, the unicast label for this particular EVI, and then we will put there the original frame. Now, obvious question can be, oh, actually, am I using the label for each particular MAC? No. We are basically allocating this unicast label per whole bridge domain, per whole EVI. Something like per VRF label allocation versus per prefix label allocation. Really, whole the bridge domain, whole the EVI will share the same label. So you will see when you will go in the lab and you will check let's say you will learn two MAC addresses, both of the MAC addresses in the same bridge domain will be advertising completely same label, because it would not scale to basically advertise the label per MAC address. One more thing which we didn't discuss is aliasing. You remember at the beginning I was saying, what can happen is that in the end of the day, I will keep learning the MAC addresses only on the 36, for example, and I will never learn the H1 MAC address on the 37, but at the same time, I want to be sure that I will be forwarding over 37, right? Because there is a multi-homing. We have ESI from control plane. We completely understand, because of the route type 1 per ESI, that I can forward this MAC address H1, which I learned here, to 36 as well as to 37. But I received the route type 2 with the label for the unicast only from 36. So even if I know in control plane that's ESI, for ESI1, which is multi-homing H1 on 36 and 37. So basically 37 can forward the frame for this MAC address with destination of this MAC address. I don't have any forwarding information. I don't have a label, which I will use it as a unicast label for router 37. For this one, we are calling it aliasing. Aliasing is just fancy name for BGP multipath. In L3 VPN world, you will use the BGP multipath. In EVPN world, we are using aliasing, but it's in the end of the day, it's completely same, right? You want to do the balancing over two egress PEs. It's the same concept. So in this case, we are advertising route type 1 per EVI. Route type 1 per EVI is really different than route type 1 per ESI. In this case, it's again per context, and it's basically saying, hey, by the way, I'm using in my bridge domain, I'm using this unicast label. And this is really for the use case where you didn't learn the MAC address on the both P's, because you cannot rely on something like this, right? You can never control how compute, how host, how CE will do the balancing towards the peering routers, right? You can control everything from the network down, but you are not controlling the traffic from the compute or from the host to you. So what will then happen when I will advertise this route type 1 per EVI? Basically, I will advertise my aliasing label, and now the question can be, oh, this aliasing label, what will be? Is it cert label? No, no, no. It's still the unicast label. So route R36 will advertise the MAC address of H1 with the label, in this case, 64004, but will advertise also completely same label as a route type 1 per EVI, because again we have the allocation per bridge domain. So then when I will receive the frame, or I will receive the one flow where I will do the hashing, and I will say, okay, I'm sending it to router 36. So one flow I'm sending with a transport label of 36, unicast label of the 36 for EVI 100, then the original frame. I will send it to 36, and then let's say I will have another flow, which based on the hashing I decided to send the 37, I will be sending it to 37. So for unicast, you see that I'm able to do the balancing. I'm obviously not applying any DF election rule on the 36 and 37 here. Last thing what we have to mention for L2, and you will see that we will then close on the L2 part, is the MAC mobility. MAC mobility is very specific for the data center use case, and MAC mobility is for the use case when I'm moving, for example, the VM. Let's say the VM here is sitting behind the compute 1, and I want to move the VM behind the compute 2. Again, when I will do this move, back to the point, I don't have any signaling from the access, right? So when I will do this move, nobody knows that I moved this VM. How the network will realize that this VM get moved? That this MAC address will show up somewhere else. And if you will think about BGP is stateful protocol, right? So L1 advertised originally the MAC address, the route type 2, because it learned on the local interface. So all the network thinks that, hey, this MAC address of this VM is available over L1. Now I move, and this VM will show up behind the L3. Oh, perfect, the L3 will advertise, but L1 basically advertised this before as well. So, who is better? Like, can I rely on the time when the route arrives and so on? Imagine that then you will go and you will restart or reset your route reflector. You are not able to control which route will come first or second, or even locally, you will restart your BGP process. You cannot rely that, hey, this route came later on, so it's more up to date. For this one, we are adding one very basic field into the route type 2. It's a sequence ID. So basically, when I will move the VM will show up here. It will come from data plane point of view. I will learn it on L3. L3 will say, hey, but I learned the MAC address from L1, and now I'm learning locally. Okay, I'm considering as a move, advertising the new route type 2 with the higher sequence ID. Before it was sequence ID 0 or 1, whatever. I will just increase. I will advertise. Whole network will receive this new route type 2 and say, okay, this is higher sequence ID. I will forward based on this information. So then L1 can go and withdraw this information. And if you will think about it, this is actually a very nice mechanism which I can use for a loop prevention. I can also detect the loop with this one. Because let's say I allow in my network the VM moves, but when the VM will start to move very quickly, it's a probably loop. So we are using the completely same mechanism. We are just setting the thresholds. You can configure particular thresholds, how many times you are allowing the moving the MAC address, and then you can configure the action, for example, for bringing down the attachment circuit. So you don't need any other mechanism to basically detect the loops in the EVPN fabric. Single active. We discussed that in the end of the day, most of the time you will go and you will use the all active multi-homing, but in some cases you want to use the single active. You want to be sure that basically it will be like per VLAN load balancing. Completely same topology. Let's first look at how the output for all active. And I will do show EVPN internal label. I will see that basically this EVI for this ESI is multi-home over 38 and 39. And I will see also the label which I'm basically using when I'm forwarding to this ESI. When I will go and under ESI configuration, under EVPN, I will change the load balancing mode to a single active. I will see that one of the devices will go to the backup state. So basically, from the remote point of view, I will be forwarding the particular unicast traffic only to the single device. Really straightforward. In this case, is just changing the load balancing mode. Obviously, you have to change the load balancing mode on both of the nodes, otherwise you will have a race condition. One of them will be signaling all active, second one will be signaling the single active. Very similar with the port active, I will go and I will configure the load balancing mode port active here. And what will happen is that on one of the bundle, in this case on the router 37, because he's a non-DF, if you will do show bundle, you will see that it's signaling out of sync. So basically bundle is down. If you remember, we discussed that in case of the port active, the router which is not a DF will signal out of sync, and the basically link will not be ready from the C as well as PE point of view. So from EVPN, it will look like really like kind of like a single home or active standby.
Can you go into details on what the access-driven does on port active?
If we can take it like offline after the session, it would be awesome, because we have another slides for the. We can definitely discuss the access-driven one as offline. So we covered the L2. As I mentioned, we also, one of the very important part of the EVPN is the integration, the L2 and L3 together. How I will do integration L2 and the L3 together is over IRB. IRB is not a new concept for EVPN. We introduced the IRB a long time ago as integrated routing and bridging. But in the end of the day, how EVPN is using IRB, there are two modes. It's a distributed Anycast gateway mode and centralized gateway mode. In the case of the distributed Anycast gateway mode, I'm configuring IRB on all the leaves, basically here. So which means that when I will receive the traffic, I directly on the leaf, I will decide if I will do bridging or I will do the routing, right? If communication between H1 and H2, which are in the same subnet, it will be bridging. If I will have another subnet, I will do the routing. This is the best solution for the data center, because in this case, you will have always optimal forwarding. You will never do any hub and spoke and so on. Another mode, which is that I will take the IRB and I will configure it, let's say, on my DCI. In this case, the leaf is doing only bridging and the routing is done on the DCI. So if you will have a forwarding between the two subnets, it will be kind of hub and spoke. It has to first go over L2 to the DCI. DCI will do the routing and will send it back. The huge also difference here is the scale requirement for the DCI, because here in this case you are distributing your adjacency table, you are distributing your MAC address table and so on, and your DCI is acting as a pure L3 device. In this case, when you have a centralized gateway, your DCI has to act as an L2 as well as L3 device, and here from the adjacency scale point of view, your ARP and ND, it will be definitely much higher than in the previous example. Question is if these devices know all the MAC addresses. Yes, they know all the MAC addresses. Yes, because in the end of the day, they are just doing L2 MAC address learning. They are advertising route type 2, as we learned in the previous examples. But the routing is happening here on the DCI. So first of all, what we need to introduce when we want to do the distributed Anycast gateway. How actually distributed Anycast gateway look like from the BVI point of view. Let's say that I have a single subnet, the orange subnet here. I will configure same BVI, same IP address, and same MAC address. Why? Because I can do, again, a mobility. Imagine that I'm VM, which is sitting here behind the compute 1. I will move the VM behind the compute 2, and VM will keep forwarding, and you want to have a same gateway. So basically, this is always the same IP address. This is always same MAC address. You will just configure it same. It's copy-paste for every leaf, for every BVI. At this moment, before we were using the route type 2 to synchronize the information about MAC forwarding table. Right now, when I'm introducing the IP, I need to synchronize also my adjacency table, my ARP and ND. How I will do this? I will use the same route type 2, which I was using before for advertising MAC, but I will not advertise only MAC, I will also advertise the IP of the VM. So based on the ARP, which was between L1 and the VM, for example, between compute 1, I learn the MAC plus IP. I will take the route type 2, and I will advertise this MAC plus IP. And again, I will use the ESI. So when this MAC plus IP will arrive on the L2, L2 will look at it completely the same way as before for MAC address. Will say, hey, this ESI is locally connected. I'm gonna program my MAC address locally, but I'm gonna also program my adjacency, which will be pointing locally to the same interface. So suddenly I'm synchronizing L2, L3 in the same route. And again, I cannot actually separate it. I cannot have one route for IP and one route for MAC address, because I need to be sure that for adjacency, I need to know the binding. Therefore, we are using the same route. And from the other side, from the reachability point of view, the L3 and L4, they will receive the route type 2 MAC plus IP, so they know that which MAC is sitting behind L2, and they also know which host is sitting behind L1 and L2. So when I have two subnets, you know, when the frame will arrive on the L1, you will decide if it's bridging or it will be routing to the different subnet. Let's go to the example. So first, what I can do, I can go. You remember before we configured advertise MAC for advertising the MAC address as a route type 2. I can actually unconfigure it, because when I will be advertising MAC plus IP, it would be redundant, right? I will advertise only MAC, and then I will advertise MAC plus IP, but the MAC is there anyway. So you can unconfigure this part when you are using BVI, because there is a MAC plus IP, and enabling advertising of the MAC plus IP is configuring host routing under the BVI. It's basically saying, hey, start to advertise the hosts which you learn from the ARP or from the ND. And you can see that I have a configuration here of the IP address and also the MAC address. Basically, both of these on all the BVIs across the leaves in the same context will be same. Then, because I want to also have this is like more for the L3. If I want to have a BGP multipath, I will do the traditional configuration of the BGP multipath in the VRF. You see that there is no any specific configuration for the EVPN. This is like what we know from the L3 VPN, and you can see that I'm not enabling any new address family towards the router effector. I'm still using the EVPN address family to signal this route type 2. The only what I need to enable here globally is VPN v4 unicast to allow the configuration of the VRF. But don't get confused. It's not VPN v4 towards the router effector. It's still EVPN address family. This VPN v4 unicast is just enabling the configuration for the VRF. So then when I will see the route type 2, you can see that right now I have not only MAC address, but I have also IP address. And now, very interesting part. If I will look at, I will receive something like the first and second label. Why I have a first and second label? Because I'm suddenly signaling the L2 context, which is my bridge domain, which we had before, but I also signaling the L3 context, which is my VRF. And my VRF has to need also some label, right? Because when I'm sending the L3 traffic, I need to be sure that I will be receiving in the VRF. I will do the lookup in the VRF. So I'm sending one label for bridge domain, for EVI, and one label for the VRF, which I just configure VRF-A. When I will do show EVPN EVI MAC, right now I will not see only MAC address, I will see MAC plus IP. And I will also see when you will see that I'm importing this host route into my routing table, and I will also see from the host route point of view in the RIP that I have this multipath. This is nothing EVPN specific. Basically, EVPN is just introducing the host routes into the forwarding table. So when we will go over the packet flow, let's say that I learned this MAC plus IP here over the ARP on the 36. So I'm advertising the new route type 2, MAC plus IP with the ESI, with my primary label and my secondary label, which is for VRF. And again, I have also my original extended community for route target for the bridge domain for EVI 100, but I also have to advertise the VRF route target. Basically, I'm really combining the L2 together with L3. Before I was signaling only reachability for the MAC address, how this MAC address forward towards me. I would normally go and let's say signal this host route as a VPN v4 with the extra label and so on, but I'm merging this information together and advertising it as a single update. We mentioned also like the centralized gateway. Centralized gateway is the configuration where I have my BVI here on the gateway 1 and the gateway 2. Again, I'm using the same route type 2 to signaling MAC plus IP and so on. I want to just show here a very basic like the configuration. What we introduce here, the concept of the access EVI, because if you will think about it, I need to somehow say from which interface I learn this MAC plus IP, because I need to have the synchronization between the gateway 1 and gateway 2, right? To do this, we say, hey, you know what, for you, the interface is actually whole this EVPN domain. So whatever you will learn from this EVPN domain, this is your ESI. So when the gateway will learn it, will advertise it to gateway 2, say, oh, by the way, we are sharing the same ESI, so we should synchronize it. So suddenly you will see the concept that before we were configuring the ESI on attachment circuit, right, on the Ethernet interface or on the bundle interface, and right now I can actually configure it on the whole the EVPN network, interface. And then again, when you will do the show EVPN Ethernet segment, you will see completely same information what you saw on the access devices when you were using the distributed anycast gateway, except right now it will be centralized on the gateway 1 and gateway 2. If you are deciding between distributed and centralized gateway, obviously distributed is the best one. If you can do the distributed, don't even think twice, because you are getting optimal forwarding, you are doing the load sharing. It's really just in case that your devices are not capable to do the IRB, or because of some reasons you don't want to do the L3 in the access. The centralized gateway obviously needs much more resources. You typically need the more capable devices on the centralized gateway and so on. So really, first think about distributed anycast gateway. One thing which we introduce with the EVPN, and I mention it, is the concept of the host routes. You can also ask why actually I need to know the host routes, right? Because if I'm in the same subnet, I'm forwarding based on the MAC address. The problem is that when I will start to do the sharing of the same subnet across the more devices in the data center, for example, I need to know this reachability information of the host to be sure that I will have optimal forwarding. Let's say that in this case, DCI1 and DCI2 would just see the subnet. So let's say that you have some subnet XXX/24. In the normal L3 VPN world, the L1 to L4, all of them would advertise this subnet as XXX/24. But when I will get a frame for where the destination address is XXXH1, then I don't know if to forward L1, L2, L3, or L4. Therefore, in the EVPN fabric, I need to also install these host routes, because I need to be sure that I know where this particular host is actually sitting. That's a new concept which we introduced with the EVPN compared to the L3 VPN. Most important here, what we will be showing at this moment, is that I'm keeping really my L2 domain only on the leaves here, right? And I will show how to integrate it with the, let's say, SP core or any one in the out of the data center. And I'm keeping the L2 context here, and the DCI, data center interconnect, is doing only the L3 forwarding. We just said that we need all these host routes, right? And now think about it. The problem is that when I have all these host routes, right, I can also say, okay, whatever, I can somehow have an IGP domain here. Let's say this is also MPLS, core is also MPLS. So let's advertise all the host routes to the remote side, and the remote side can then directly forward to the L1, L2, L3, L4, and I don't need any DCI, because it's MPLS end-to-end, and I don't have any problem. There is one problem. This thing will probably not scale, right? If you will go and you will start to advertise the host route of all your VMs or your containers, whatever is sitting in the data center, everywhere in your network, it will definitely not scale. You will need to summarize somewhere, most of the time. So what is happening? We are typically summarizing here on the DCI1 and DCI2. So this domain, this EVPN domain, has all the host routes from the leaves. The DCI will install this host route into the forwarding table. But towards the core, you will advertise only the subnet. But the subnet will be advertised with the next hop of DCI1 and DCI2. So when you will be then forwarding, let's say, the CE, like let's say some customer device, something in your cloud, and is forwarding some traffic to, let's say, to H1. You will send the traffic to PE3, or let's say DCI3, doesn't matter. The PCI will do the lookup, will send it to DCI1, DCI2. DCI1, DCI2 will do again the lookup, and will see the host route and can then forward to the right device. Because if you would not have a host route, again, you will have a problem that you don't know if to send it to L1, L2, L3, or the L4, and basically you can have a black holing, or at least non-optimal forwarding. So right now, how to do the stitching like this? Because DCI is actually in the middle. So you have multiple options. You can use the VPN v4, VPN v6, as we know in the core. You can theoretically also use the VPN v4, VPN v6 in the EVPN domain, right? Because theoretically, your DCI doesn't need to know any L2, so you don't need to know any ESI, any route type 4, any BAM labels, and all the things which we just learned, right? You just need the IP forwarding information. You can directly do it like EVPN end-to-end, so you will have EVPN domain here, EVPN domain here. Or you can combine both, VPN v4, VPN v6 here in the core, and EVPN in the data center. The reason why I'm showing these three options is that when you will go, most of the time, you have some existing core VPN v4, VPN v6 in your network. Right? You introduce EVPN in the data center. You have to use the EVPN at least between the leaves for this all L2 multi-homing and DF election and all the stuff which we just learned. But this is, in the end of the day, best way how to integrate two different solutions together that you don't have to touch anything in your existing VPN v4, VPN v6 core, and you will just introduce EVPN into your, let's say, CO or the part where you need to do the L2 multi-homing and L2 forwarding. If you will look at, and we will just summarize, basically every solution has some cons and pros. There is no such a thing like one solution fits all. Right? The reason why I was listing also all these three options is basically for you to have a chance to compare and basically be able to decide which one will be best for you. But in the end of the day, in general, you will realize that the best is, most of the time, the best one is to really combine these two together, VPN v4 and EVPN together. Because if you will think about it, when you will start to advertise only L3 informations, it doesn't matter if it's VPN v4, VPN v6, or EVPN. The information itself is the same. It's English versus Spanish, right? In the end of the day, it's just yet another family in the BGP. Still the same thing. If you want to advertise hold the prefix in EVPN, something like before we had this XXX/24. In EVPN, we are using the route type 5. And route type 5, if you want to enable route type 5, you will just go under address family L2 VPN, EVPN, and you will say advertise VPN v4 unicast. So basically, you are telling to EVPN, hey, what normally we would advertise as a VPN v4 unicast, take it as a route type 5 and advertise it. So basically, then you are getting completely same thing. You can really decide if you want VPN v4 or you want to route type 5. It's completely same thing. Same information inside the boat. I have this EVPN route type cheat sheet. We will not definitely go over it right now. It's there. I can see that someone is making picture. Again, you will have a chance to download these slides. You don't have to make pictures. Really, use this one once you will be learning, because obviously it was a lot of information which we go over today. When you will go and then you go step by step, you will want to understand all the routes. Try to go over this cheat sheet and try to say, oh, I exactly know why route type 4 is advertised and why I have a extra EVI label here, why I have a label here, how the bridge domain with the EVI2 can talk to VRF over the BVI. All these details, if you will really understand, in the end of the day, you are getting the whole concept of the EVPN. But really, pay attention to the first part of especially for the L2, route type 1, 2, 3, 4 are the really most important to understand the concept. Once you understand the concept, you will see that the things are keep repeating. I want to talk quickly about VPWS, because we talk about EVPN ELAN also multi-homing. With EVPN, VPWS, the cross-connect, I can still use the multi-homing, but obviously I don't have any bridge domain because it's basically like a virtual wire. I'm still cross-connected. I'm doing the multi-homing, but I don't need route type 2 because there is no any MAC address learning. I don't need route type 3 because there is no any broadcast, and unicast, and multicast traffic. So I'm just using the subset of the route. In this case, it's mainly route type 1 for advertising the service. In case of the EVPN VPWS, we need extra extended community because, especially for the single active. Before, with EVPN ELAN, how I will know when I'm using the single active, and basically I'm the remote router, right? And I'm peering, there are another two who are advertising me this route type 1 per ESI. They are saying, hey, we are using the single active. Perfect. I know that only one of them is forwarding. But how I will decide who? I don't know who is the DF because DF, it's their thing. I don't know it. I know it based on the MAC address. Who advertised the MAC address? If the P1 will advertise me the MAC address and say, hey, we are single active, which means that he's the one who can forward the traffic, not the second one. But the problem with EVPN VPWS, because I don't have a MAC address learning, if these routers will advertise me that they are doing the single active, I completely don't know who can forward. So for this one, we introduce extra extended community where we are signaling the primary and backup bit. This primary and backup bit is basically telling me who is active, who is standby. Just to give you the hint, in the new 7432 base EVPN, we will be also introducing we are introducing the same extended community for ELAN as well. So moving forward, you will see that also this extended community will get implemented for the ELAN as well to be sure that it's a consistent. Together with this extended community, as I said, primary and backup bit, we are also signaling if we are using the control word for the L2 services. And the last one is also MTU. So basically, I can theoretically have synchronization of the MTU. So I can decide when some MTU is not aligned with what we are signaling. The configuration is then simple. As you know, the point-to-point cross-connect, before you had the neighbor, pseudo-wire ID, and so on. Here we have neighbor, EVPN, you say which EVI ID you will be using, and then you will have also the service ID. Why I'm using the service ID? It's basically I can take multiple EVPN VPWS services and multiplex them into the single EVI ID. So basically, I don't need to allocate for each of the EVPN VPWS circuit. I don't need to allocate unique EVI ID because I have like basically subset service ID. So I can really bundle multiple of the EVPN VPWS from the signaling point of view into the same EVI ID. Once you will start to do the design with the route targets and so on, you will see some of the benefit because each of the EVI is allocating the separate route target, right? So if I'm able to bundle multiple services into the same basically EVI ID under the same route target, it can have some benefits, especially when we will talk about BGP and basically optimizing the BGP in the network. If I will want to check the service, show L2 VPN cross connect, I can also check from show MPLS forwarding, but basically I have all active multi-homing here from the cross connect point of view. Quickly single active. Basically, the configuration is the same, except I will configure under the ESI. I will configure the single active. In that case, I'm sorry for that. In that case, I will go under show MPLS forwarding, and I will look at the label which I'm using for this cross connect. I will see that one of them is standby here. Again, same principle as we had before with the single active for EVPN. If we will look at the detail of the route type 1, which is signaling this EVPN VPWS service, as we discussed, we have this MTU, and we are signaling the control word. You will see that you are receiving these two routes from the two remote routers which are doing this single active multi-homing. One of them is primary, one of them is backup, so I know to which one I should forward the traffic because again, I don't have any MAC address learning. My favorite part is the migration of the VPLS to EVPN. because it's really, really simple and really nice. So imagine that you have your existing VPLS domain. As we discussed, you have a full mesh of the pseudowires, and you want to go step by step and migrate this network to the EVPN. So first, I have this configuration of the VPLS. What is very important in the iOS XR, the VFI or core interface is always in the split horizon group 1. What does it mean? If I receive anything from the core, I'm never sending it back to the core to basically protect the loop, right? In case of the VFI. So basically, I have all these pseudowires are up. So whatever I will receive from pseudowire towards the 37, I will never forward to 38. That's basic principle. Then I will go and I will configure in the same bridge domain. I will configure EVI 100. What will happen? Nothing, because I don't have this EVI 100 anywhere else. But at the same time, EVI 100 is also in the split horizon group 1. So I know that I will never get any traffic between the VFI and EVI. So I'm sure that there will not be any loop. I will go on the 38, and I will do completely the same thing on the 38. I will configure EVI 100. 36 and 38, they will start to advertise this EVPN route between each other. Once I will receive the route type 3 mainly, in the control plane, I will go and I will bring down this pseudowire towards the 38. So basically, when I will forward then from the CE1 from CE1, let's say to CE3, I will use the EVI 100, basically EVPN forwarding. But when I will go CE1 to CE4 or CE2, I will go over VPLS. And then I will go step by step. Once I have basically all the pseudowires down, I can go and I can unconfigure my VFI, so I'm forwarding just based on the EVPN. Yes, please, there is a question. I cannot hear you. Tell me.
You mentioned EVI is horizon group 1, although in the configuration it isn't. It's outside VFI 1.
Okay, the question is if the EVI 100 is in the split horizon group 1 all the time. It's every single time, but in iOS XR, you don't have to do any changes. Once you will bring any of these core interfaces, you will configure them. They are automatically, by design, in split horizon group 1. You don't have to do anything. So this thing that even if you will do any misconfiguration, you will never have a loop from the core. Never ever it will happen. The last thing which I will cover here, and then as I promised, I have a lot of things for you for offline studying, is the interconnect. If you have a network which you know that you will not be able to migrate into the EVPN, you will want to still interconnect it. The reason why I wanted to show this example is, again, because I promise you that you will see the pattern, that things are starting to be like the similar, right? In this case, we have some legacy network, which is VPLS, will probably never become EVPN because these devices, A1 and A2, they don't support the EVPN. At the same time, I have some EVPN network, I have my multi-homing here with the C3, and I want to use this 36 and 37 as a gateway between these two domains, between VPLS and EVPN. If you will think about it, one of the first slides which I had, I was saying, hey, with VPLS is a problem because I have to take care of the multi-homing, because if I will not have any multi-chassis LACP, I will not have any active backup pseudowire, I may introduce the loop, or I can introduce the duplicity in the VPLS domain. If you will think about it, from the EVPN point of view, all this VPLS domain is like a single active network. Because I know that MAC address can come from only one device. If I'm sending the broadcast, unicast, and multicast traffic, I know that it can go only to the one interface. There cannot be because otherwise I will have MAC address flip-flopping. So I will take this VPLS, I will say, this VPLS domain has a certain ESI, and is a single active network. And everything else is the same as we learned before, from the signaling route type 2, route type 4, route type 3. Everything is the same. For this one, we introduced the concept of access VFI, right? Because you remember, VFI and EVI are in the same split horizon group, so I would not have a forwarding between them. So I need some new interface, which is not in split horizon group 1, because I need a forwarding between EVI and VFI. And in this case, I go and I will configure this VFI with the Ethernet segment, right? And I will say, this one is single active because it's a VPLS. So this was just an example how we keep reusing the same principle in the EVPN. And if you will go and you will start to study the E3, which is there. If you will look at also this BGP offload, PC offload, which I'm keeping there also for the extra learning, you will see that the same principles are keep repeating. I completely understand that it was not possible, to catch every single detail what we are just discussing. But I believe that when you will go over it a couple of times, if you will go into lab, you will try it in the control plane. I believe that you will after this session, you will understand the basic principle for the EVPN. As I promised, I have some offline learning. This is the BGPPE control plane offload. You will see the benefit of the EVPN there. I will keep it there for your extra learning. Just very quick summary, because we are running over the time here. Extra learning we just mentioned. In the end of the day, it's important to understand that EVPN is not automatically the replacement for all the address family. It's just a complement. It's all about the BGP. So EVPN and VPN v4, VPN v6, they can run together. They can be together as a really like a friends. And at the same time, with EVPN, we learn a lot from the VPN v4, VPN v6. Most important, EVPN all active multi-homing. And if you will want to also know more, you can go and you can visit e-vpn.io, where it's mainly a lot of DCI use cases and so on. And again, look at the more slides in this presentation. Hopefully it will be helpful. And thank you that you spent the time with me, all the 90 minutes. And I'm sorry that I'm a little bit over. Thank you very much.